So given two matrices A and B in M and K, how do we decide whether or not these two matrices are similar? We'll see in this lecture how to solve this decision problem. Okay, so remember that given a matrix A, we can define an KT module MA. So this is KT module. It's as a vector space. It is just Kn as an additive abelian group, and we have the action of a polynomial defined by PTV equals PA times V. So here we are thinking of V as a column vector, an element of Kn as a column vector, and then you can just evaluate the polynomial P at the matrix A, and that will evaluate to an n by n matrix A. You can just multiply that n by n matrix on the right by this column vector to get another column vector. And similarly, we have MB is Kn, but now PTV. So maybe here I'll write a dot A, here I'll write a dot B. That means the module structure in MB is PBV. Okay, now suppose that F from MA to MB is a KT module isomorphism. So what that means is that F is homomorphism from Kn to Kn. It's an abelian group isomorphism, and it also has the property that F of PTA V is equal to PT dot P F V. Okay. Now suppose that we can write F as, so F is just a linear map from Kn to Kn. We should be able to write it as a matrix. So suppose we have that F of V equals XV for some matrix X, and this has to be invertible because F is an isomorphism. So then this equation here becomes X PA, this PTAV is PAV, is equal to PB XV, or we can rewrite this as X PA X inverse. So is equal to PB as matrices, because this thing up here is saying XPA is PBX as matrices. So what we're saying is XPA X inverse is equal to PB as a matrix, and this is true for every. So here itself we should say for all PT belonging to KT. In particular, if we take PT to be just the matrix T, then this implies that XA X inverse is equal to B, which is the same as saying that XA is similar to B. So what we've seen is that if MA is isomorphic to MB as a KT module, then A is similar to B. Conversely, suppose A is similar to B, then there exists X in GL and K such that XA X inverse is equal to B, but this also means that XPA X inverse is equal to PB for every P in KT. I'll let you think about why this is true, but basically you have to expand this PA in terms of powers of A, and each power will also get conjugated. So the point is that x a to the n x inverse is equal to b to the n if x a x inverse is equal to b. So you have to use this. Okay, so then this implies that, so defining f of v to be xv gives an isomorphism, a KT module isomorphism from MA to MB. So the upshot of this is the following theorem, that if you have two matrices A, B in M and K, then A is similar to B if and only if the module MA is isomorphic to the module MB. The KT modules MA and MB are isomorphic. Okay, now let's see how we can turn this into a way to decide if two matrices are similar or not. So remember that MA, this module we've seen, is isomorphic to KT to the power n mod column space of Ti minus A. We saw this last week. And MB similarly is isomorphic to KT to the n mod column space of Ti minus B. And we've also seen that when matrices are expressed in this form as generated by a certain free modulo the column space of some matrix, then those modules are isomorphic if and only if the corresponding matrices are equivalent. So MA is isomorphic to MB if and only if Ti minus A is equivalent to Ti minus B. And so, but then we can check if two matrices are equivalent by just computing their Smith normal forms. So what we get is A is similar to B. So that means MA, that's equivalent, we've seen, to MA being isomorphic to MB, which is equivalent to saying that Ti minus A is equivalent to Ti minus B. So this is if and only if the Smith form of Ti minus A is equal to the Smith form of Ti minus B. So given two n by n matrices, we can decide if they are similar or not by computing the Smith forms of the corresponding matrices Ti minus A and Ti minus B. So this is, you can think of this as an algorithm to decide whether or not two matrices are isomorphic, are similar. Okay, let's just look at this with a couple of examples. So let's look at two matrices and we'll decide whether or not they're similar. So I'll start with a very simple example. Let's take A to be the matrix 1, 0, 0, minus 1 and B to be the matrix 0, 1, 1, 0. So at the outset these matrices look kind of different, so maybe they're not similar, but let's just work it out. So we have Ti minus A, so what is that? So Ti minus A is T minus 1, 0, 0, T plus 1. And what's its Smith normal form? So remember, to compute the Smith normal form, so the Smith normal form is something like this: D1, D2, Dr, and then 0, 0, 0. and the product of the first I diagonal entries is the GCD of all the I by I minors. So we just need to figure out the GCD of the I by I minors of this 2 by 2 matrix. So firstly, what are the GCD of all the elements of this matrix? Well, that's clearly 1 because we got T minus 1 and T plus 1 and their GCD is 1. So the first element is 1. And then the GCD of the 2 by 2 minors divided by the GCD of the 1 by 1 minors will be what comes here. With the 2 by 2 minor, there's only one, namely the determinant of the matrix, and that is T squared minus 1. So the Smith form of Ti minus A is 1, 0, 0, T squared minus 1. Let's work out the Smith form of Ti minus B. So here we have T minus 1, 0. Once again, the GCD of all the entries, oops, I should write equivalent to. So the GCD of all the entries is 1 and the determinant is, I'm sorry, this is not 0, this is T, is again T squared minus 1. So indeed, Ti minus A is equivalent to Ti minus B, hence the conclusion is that A is similar to B. Let's just look at one more example. So let's look at 3 matrices this time, 3 by 3 matrices. So let's take A to be the matrix 0, 1, 0, 1, 0, 0, 0, 0, 1. B to be the matrix 0, 0, 1, 0, 1, 0, 1, 0, 0. And C to be the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0. So now we have Ti minus A is T minus 1, T 0, 0, T minus 1, 0, 0. And this is the case. So as in all the examples we've seen so far, the GCD of the entries is just 1. And now let's look at the 2 by 2 minors. So here we've got a 2 by 2 minor T squared minus 1. Here we've got a 2 by 2 minor T into T minus 1. And then here another, so there are actually 9 2 by 2 minors here, and many of them are 0, but if you just go through them carefully, you'll see so for example, if you take the second and third row and the first and third rows and the second and third column, then you get this minor 1 into T minus 1. So you get minus T minus 1. So T minus 1 turns out to be the GCD of all the 2 by 2 minors. Every 2 by 2 minor is divisible by T minus 1. And to compute the third element on the diagonal, we just have to compute the determinant of this matrix and divide by T minus 1. So the determinant is a block diagonal matrix, so the determinant is easy to compute. It's T squared minus 1 into T minus 1. So dividing by T minus 1, we get T squared minus 1. And let's look at Ti minus B. So that's the matrix T0 minus 1, 0, T minus 1, 0, 0, 0. Did I miss something? There should be a minus 1 here. And again, you can think it through. You'll see that there's the same kind of behavior, that you have 1, 0, 0. All the 2 by 2 minors are divisible by T minus 1. And the determinant of this matrix is also T squared minus 1. So A is similar to B. What about C? So we'll have T, 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 0, minus 1, minus 1, 0, and we have 0, minus 1. So the GCD of all the minors is 1, of course, but even the 2 by 2 minors I have 1. So for example, this bottom left minor here is just minus 1, so up to a unit it's 1. So the first two factors are 1, the diagonal entries in the Smith form, and the last entry is just going to be the determinant. So you have to work out the determinant, and you can check that it is t cubed minus 1. So what we see is that A is similar to B, but these are not similar to C.